Hello Quantum Tech HD family. In today's video, we will join the legendary construction of a dream house. The project starts with careful site preparation, forming a wide, level base of compacted sand. Immediately after establishing this base, we begin burying the sewer piping network across the entire footprint. The key point here is sequencing, so the piping is buried in the sand before any insulation is installed. Only after the underground piping is installed and stabilized do we proceed with the thermal structure. We assemble insulated permanent formwork panels around the perimeter, creating a rigid boundary for the foundation. Here, the buried sewer network has been fixed into the sand base, and the slab perimeter is formed. The slab perimeter has been formed into an insulated bathtub that will hold the concrete and heat. The insulation field is refined first, with boards fitted across the footprint, paying close attention to seams. With the insulation locked in, we begin installing the communications penetrations and internal routing for the house. Multiple pipe exits and conduits are positioned vertically through the insulation for the underfloor heating system. This allows us to establish the precise locations where the future boiler room and technical areas connect. The cold and hot water supply lines are routed so they emerge exactly where fixtures are installed. This routing strategy matters because it reduces later wall chasing and keeps the structural masonry intact. Large coils of red pipe are unrolled across the slab area, laid out in controlled patterns. The pipework is fixed into position using a grid of supports so it cannot float during concrete placement. As the heating loops expand, we integrate the heating system with the slab's reinforcement strategy. The reinforcement mesh is expanded and closed into its final working configuration before the concrete pour. We position steel bars and mesh sheets so they overlap correctly, forming one continuous grid. Concrete always shrinks as it cures and expands and contracts with temperature cycles. In a heated Swedish slab, this movement is more pronounced due to thermal loading from the heating system. With the reinforcement stabilized, we complete the central mechanical hub of the slab, the collector manifold. Each heating loop must have a controlled length and flow resistance for uniform heat output. At the same time, we begin preparing the slab for the concrete finishing phase and geometry. We then complete the Swedish foundation, building the insulated blind area around the house. This perimeter treatment is one of the most important pieces, extending the thermal and drainage strategy. By keeping the soil warmer around the perimeter, the blind area stabilizes the ground and reduces movement.
With the foundation finished and protected, the house finally begins to rise above ground.
We use aerated concrete blocks, also called AAC or gas concrete, for the first floor masonry. This is a material strongly associated with modern Eastern European residential building. Structurally, it is lighter than traditional brick or solid concrete block, reducing foundation load.
Thermally, it provides better insulation due to its cellular structure, and practically, it allows precise shaping.
However, it performs best when loads are distributed evenly and when tensile stresses are controlled.
We use manual force and a mallet to seat blocks into mortar, ensuring full contact.
In this sense, voids under blocks are dangerous because they create stress concentrations. Instead of loads being spread evenly, they concentrate at contact points, increasing the risk of cracking. Thus, our approach shows correct masonry physics. Continuous bearing is more important than speed. We establish the wall lines and openings, Then begin laying blocks in controlled courses. Also, as you can see, the reinforcement also becomes essential as we prepare the top of the wall. The reinforcement prepares the masonry to interface correctly with the reinforced belt that will follow. For the ring beam to truly work, it must be mechanically integrated with the masonry beneath it. As the walls define the building's perimeter and internal layout, we begin expanding the usable footprint. That is why we build the terrace as a separate load-bearing timber structure supported on piles. The main beams are then installed, including large section timber as primary load carriers.
These are then complemented by secondary beams for infill framing across the deck area.
Here, primary beams define spans and stiffness, while secondary joists control spacing and deflection.
Once the beam field is completed, the deck is closed using 18mm OSB sheets for a solid floor.
At this point, the building must be prepared internally to receive its engineering systems and finishes.
We begin by preparing the aerated concrete block walls so they can accept communications cleanly.
This is why we use a grinder and cutting tools to form precise channels and recesses in the wall. After the fittings are installed, the pipes must be recessed into the wall so the surface is flat. Also, because aerated concrete absorbs moisture aggressively, surface chemistry becomes just as important as mechanical work. Priming here is not optional, as it controls absorption, stabilizes dust, and ensures bonding compounds cure correctly. Once the walls are technically prepared, the project moves into the decorative but still highly technical finish stage. We apply AMK, a Russian-produced wall cladding material, where each brick is made from natural marble chips. The significance of this system is that it mimics brickwork while functioning as a bonded composite surface. The adhesive fills and locks the joints, and the brick modules create a stone-like aesthetic.
Each brick is protected with a film during installation, which must be removed only after curing.
Next, for the second story, once the primary beams are positioned, we install the internal members. These joists are set in repeated intervals, producing the ladder structure that becomes the skeleton. Once the deck is stable, we begin fabricating and positioning the large wooden wall frames. These wall elements are assembled from dimensional lumber into full-height panels with studs and openings integrated. This means that they are designed to be raised into position like prefabricated units, reducing errors. Instead of building piece by piece vertically, we can square the frame while it's flat, then lift. When the first wall is raised, the process becomes a controlled choreography of rotating panels. As you see, one person stabilizes while another pushes the panel upright, rotating it from horizontal. The wall is temporarily braced so it cannot lean, as every upright frame behaves like a sail. With one wall upright, the next frames follow, each one locking into the platform and aligning. The second story is being born, not through decoration or finishing, but through disciplined creation. For the roof, we first establish its geometry by positioning the long inclined rafters that define the slope. In architectural physics, this allows the roof to resist deformation, becoming a bracing structure as much as covering.
The rafters are installed in repeated spacing, creating a rhythmic skeletal field that transfers loads down.
This spacing is not arbitrary, as it controls the stiffness of the roof and prevents flexing. With the rafters in place, the next step is to close the roof structure using a continuous deck. Instead of OSB alone, we install long timber boards across the rafters, forming a full wooden skin. After the membrane is installed, we continue refining the roof edges, especially the overhang zones. We begin installing large, rigid insulation boards directly across the sloped plane, placing them in wide fields. The purpose is to build a thermal envelope that remains uninterrupted over the top of the building.
These are laid in a staggered pattern, minimizing continuous seams and fitting each panel tightly.
Where boards meet at the ridge, we seal the joint using expanding foam, effectively welding it.
With the battens complete, the roof is ready to be closed, so we begin laying OSB sheets. One of the most important interruptions on that surface is the roof window, where precision matters. Before waterproofing begins, we prepare the skylight assembly itself, ensuring a perfect fit in the opening.
Once the window is positioned into its prepared opening, we fasten it down carefully and securely.
We unroll large blue waterproofing sheets across the OSB surface, pulling them upward along the slope.
Each sheet is overlapped with the next to form a drainage hierarchy, so water is directed. In this sense, we ensure the roof is symmetrical not only in shape, but in performance. Still, there is a lot of work to be done to finish the roof, such as refining its perimeter. We focus especially on the eaves, because the eaves line is where gravity and water flow converge. These details are not cosmetic. If the eaves are not rigid and straight, the roof plane will ripple. A black strip of bituminous material is applied along key lines, especially at joints and edges.
We spread roofing mastic and bed the strip into place, creating a tough, water-resistant belt.
Then the final roofing begins. Asphalt shingles are installed in clean rows across the entire surface. We start from the lower edge and move upward in a disciplined pattern for maximum protection. This is slow work because it demands precision. Shingles must be trimmed cleanly and fastened. The key engineering idea is that this roof is built as a multi-layer drainage and protection assembly. In climates where snow sits for weeks and rain arrives in storms, the roof must assume water. So we build a system where, even if the outer layer is challenged, water is redirected.
For snow performance, shingles are especially effective because they create a surface with high friction.
But the roof is only as good as its edge drainage, so we install the gutter system. That repeated spacing is not aesthetic. It ensures the gutter can carry heavy water flow and debris. A sagging gutter becomes a pond, and a pond becomes ice, and ice becomes structural tearing. Thus, the gutter is engineered to capture runoff from the entire roof plane and redirect it away. This matters because wooden walls and roof overhangs fail not from rain hitting them once, but wetting.
If runoff drips uncontrolled, it saturates the fascia boards, stains the cladding, and creates a rot zone.
We now shift from the roof surface itself to the second-story facade, focusing on closing the gable. To this end, a large white protective membrane is stretched across the entire open facade area.
We then proceed to the permanent thermal closure of the gable wall by installing rigid insulation panels.
Each board is lifted into position and pressed into place, gradually covering the wall area in sections. As the insulation rises toward the roofline, we carefully fit the panels into the sensitive junctions.
At the same time, exposed timber elements under the roof overhang are treated with protective coating. At this stage, the balconies are already structurally there as an external platform projecting from the envelope. However, we still have to turn that raw structure into a functional balcony system for the house.
This frame is made from heavy boards and joists set perpendicular to the facade, creating the skeleton. The key here is that the balcony is not treated like an independent porch. It must be connected. We apply a continuous waterproofing layer across the entire balcony plane, sealing it like a roof.
The membrane must run up the wall junction and terminate properly at the outer edge for drainage.
This is the difference between a balcony that lasts decades and one that fails in 2 winters. At this point, we must delve into the importance of this project, as this is not simple.
We are not simply building a house, but building a long-term answer to a question many never solve.
And this question is, what does a life built by your own hands actually look like? We indeed live in a world where housing is often reduced to quick real estate transactions and plans. Our dream house becomes something fundamentally different, as it becomes a physical declaration of values.
The house is the product of planning, discipline, and the courage to invest time into something meaningful. What makes the project meaningful is that it is not based on shortcuts or temporary fixes.
Our methodology shows a builder who understands that true comfort is engineered, not purchased. Ultimately, this project matters because it is a human story told through engineering and rare combination.
As you may have seen, most dream house narratives lean on fantasy and instant results.
We can see big spaces, pretty finishes, cinematic shots, and the illusion that a home appears. But our story goes in the opposite direction, focusing on the reality of the work.
Like before, we are executing a facade finishing technique that creates the appearance of precise masonry.
However, as we told you, we do so without paying for real-facing brick or clinker.
The brick effect represents economic intelligence, a beautiful illusion that saves money and time.
Meanwhile, the timber cladding represents craft and identity, a material that requires patience and pride. At this point, the facade already carries a strong identity through the contrast between surfaces. If the openings are refined with the same timber, the house gains continuity and language.
This matters because facades often fail visually when they look like separate systems stacked together.
But here, the wooden trims can act as the connector that makes the building coherent.
These become deliberate accents that visually anchor the structure and introduce a third plane.
The brick finish provides the base character, while the timber provides the upper character.
The result is a facade that feels both engineered and welcoming, a perfect balance of materials.
Even the color choice matters, as we use dark-stained wood against the lighter wall surface.
This, as you can see, creates a strong framing effect around openings and edges. The wood becomes an outline, almost like a graphic border, making the structure look architectural.
You can literally see the builder's hand in the alignment, fastening, and finishing of every piece.
And the real aesthetic strength comes from how these two finishes balance each other perfectly. Brick effect render can look very uniform and flat if it covers everything without relief. Instead of seeing an uneven wall texture, the eye is guided by a strong border.
They correct perception because it frames the opening like a picture frame and controls vision.
It proves that we are building a house that communicates seriousness through every small detail.